Hey everybody, so welcome to our first video for Unit 2, which is all about intramolecular forces and lattice energy. Now, before I get started, I just need you to know that this is now the third time that I'm filming this video. I lost it the first time. The second time I recorded the wrong screen. And hopefully the third time's a charm, right? Because this is ridiculous how many times I've talked about lattice energy the past week, especially to myself in a room alone. Yes, hopefully there's no glitches with this. Anyway, before we get into lattice energy and potential energy, I just want to talk a little bit about the three basic types of chemical bonds. So I'm going to assign one of the YouTube videos that you'll watch at home, and then you'll take a quiz on that, which is all about the three basic types of chemical bonds. And that's because we talked about that in Chem 1 already, so we don't need to really take a lot of time to talk about those three types of bonds in detail during class. But there are three basic types of chemical bonds that you need to be familiar with, and those are the ionic bond, you have the covalent bond, and we also have the metallic bond. And there's differences between them that make them all, unique to one another. It has to do with their electronegativity, which you'll learn about in the video. But there is a key difference between each of these that I think is really the best way to identify the types of bonds. And the best way to tell whether something is an ionic bond or a covalent bond is just by looking at what type of elements make them up. So for ionic bonds, the best way to tell if something has an ionic bond between them is because these are going to be between your metals and your nonmetals. And that's because they have a very large electronegativity difference. Your nonmetal can steal that electron from the metal because it has such a stronger attraction for electrons. So this is between a metal and a nonmetal, whereas covalent bonds are going to be between two nonmetals. And that is because they both have similar electronegativities. So neither one of them wants electrons that much more than the other. Therefore, they can both hold on to those electrons. So they will share their electrons. We'll just write share electrons there. Ionic bonds transfer their electrons, whereas metallic bonds, on the other hand, are typically between metal and another metal. So this is between anything that is holding metal ions together. So if you have a copper penny, there are metallic bonds holding them together. On the other hand, you could also have alloys of two metals, which is just a mixture of more than one type of metal that's been melted down next to one another. In this case, these are being held together by the sea of electrons. Sea of electrons, which I talk more about in those videos, in that video that I asked you to watch on your own. Now, all three of these types of bonds are what we know as intramolecular forces. And this prefix here is very important. So those are intramolecular forces. And this means that they are the forces that hold atoms together in a single molecule. And that's what intra means. Intra means within. So you might recall from Chem 2 talking about intermolecular forces. Inter means between. So we were talking about hydrogen bonds and dipole-dipole. They're between two different chemical species, whereas intramolecular forces are holding together the atoms within a single molecule. So this would be, for example, what's holding together that oxygen and hydrogen in water. That's an intramolecular covalent bond. So this particular unit is all about what's holding together the atoms within one single molecule, formula unit, or structure, right? So just key difference, intra versus inter. Why do atoms bond to one another in the first place? Well, atoms bond to one another to lower their potential energy. we've talked about before. So they want to become more stable. They want to satisfy the octet rule. And not that those are wrong, but in this case, I think lowering their potential energy is a much better way of saying that. Because technically, we can't really show that atoms want 8 electrons in their outermost shell. There's no way for us to really measure that. We also can't really measure stability, but we can measure potential energy. And when we measure potential energy, we have found that atoms are the most stable when they are a specific distance away from other atoms. So here are 2 hydrogen atoms, right? So hydrogen is a nonmetal. Nonmetal bonded to itself gives us a covalent bond. So in this case, hydrogen is held together via covalent bonding. So we can make a note of that up here. Covalent bond between 2 hydrogens. So, okay, we want to know what is the perfect distance between each of those hydrogen atoms. Let's take a look at this section first. Hydrogen likes to bond to one another because if they're not bonded to one another, they actually have a higher energy than they do when they're not bonded. We already know that they're not stable. We know that they don't have a full outer shell, which is really why they're not bonding. But what it comes down to is that their energy is higher as opposed to that. Because remember, we can measure energy. So as I look on my y-axis, energy is the highest right here, highest energy. And down here is the lowest energy. And here is internuclear distance. So remember if we just said intra is within, inter means between. Nuclear, you've heard that word a lot already. The nucleus or nuclei. So internuclear distance is the distance between 2 nuclei. So the distance between the nucleus on one hydrogen atom and the nucleus on the other hydrogen atom. When they're too far apart, they have too much energy, right? They're not very stable at that point because they don't have that full outer shell. On the other hand, as these hydrogens creep closer to one another, notice that their energy is going down, their potential energy, until we reach this low point right here. This is the most important point on the graph, and that's because this is where your potential energy is the lowest, right at this point. And that particular spot on my x-axis corresponds to the bond length. So this would be the distance between those 2 nuclei right here. This bond is 74 picometers long. If those nuclei start to come even closer to one another, you'll see that this potential energy shoots up really quick. We know that these nuclei are positively charged, right? Positive and positive. If those 2 positively charged nuclei get too close to one another, what do we know about positives and positives? They're going to repel one another. So if these 2 nuclei get too close to one another, they start to repel. So these repulsions will dominate. They want to get away from each other. Their energy is too high. They're like, get away from me. I don't want to be near you. So they want to be farther apart from one another. When the repulsions dominate, this is a very unstable state. In the same way, if they're too far apart, this is also unstable. Granted, it's not as unstable as when their nuclei are on top of one another, but they're still pretty unstable. And this lowest point is what you want to look for in these graphs, and that's because it's where potential energy is the lowest. So we'll say here, potential energy is the lowest. And that corresponds us to the bond length right here. So potential energy is the lowest. Bond length, 74 picometers. And that's all you really have to know about these types of graphs. You just have to know the bottom of the graph is where your bond length is going to be. So let's use this to talk about the strength of the intramolecular ionic bond. How can we tell what ionic bond is stronger than another? And one way to assess how strong an ionic bond is by looking at their melting points. So we know that ionic substances tend to have very high melting points, and that's because it's very hard to break those ionic bonds. However, we can also decipher what substances might have higher melting points than others just based upon Coulomb's law. So there it is. There's a nice little Coulomb's law reference again. This is huge in this class. We know that F is the force between the particles, whereas Q1 and Q2 are the charges, right? Because we know opposites attract. And R squared is the distance. Let's consider this. We're going to talk about this first part here, number 1, and we'll also answer sample problem 1 at the same time because it kind of goes together. So number 1, we have our charges and our distance. Let's talk about this. The higher the magnitude of charges, the higher the magnitude. So you might be like, what the heck does that mean? Well, that's what we're going to talk about. The higher the magnitude of charges, the stronger the forces are between them. So what does that mean? What do we mean, the higher the magnitude of charges? Well, it's actually exactly what sample problem 1 is having us look at. So NaCl, ionic substance, we know because it's a metal and a nonmetal, melts at 801 degrees Celsius, whereas magnesium oxide melts at 2,852 degrees Celsius. So holy moly, magnesium oxide has a significantly higher melting point. And melting point is a good judge on how strong the bonds are because, of course, to melt it, you have to break those bonds to separate them. Account for the difference in melting point using Coulomb's law. We have to think about this in terms of Coulomb's law. And in this case, I think the best way to start analyzing the strength of ionic bonds first is to think about the magnitude that the charges have. What do I mean by that? NaCl has a magnitude of charges as +1 and -1, right? +1, -1. So sodium's +1 and chloride is -1. However, magnesium oxide has a charge of +2 and -2. This is why magnesium oxide has such a higher melting point, is because it takes significantly more energy to break that +2 and that -2 charge relative to that +1 and -1 charge. This section has the higher magnitude of charges. Higher magnitude of charges. The +2 and the -2 will attract each other more strongly than the +1 and the -1 of sodium chloride. Therefore, the melting point of magnesium oxide is much, much, much higher. So that's our relationship based on Coulomb's law. Like I told you, I filmed this now for the 3rd time. I have this typed out already. So I am just going to paste this from my last one. And there it is. So magnesium has a charge of +2. Oxide has a charge of -2. Because these are of higher magnitude of charge relative to sodium with a +1 and chloride with a -1, they more strongly attract one another. And therefore it takes more energy, which has a higher temperature, to melt. I actually went ahead and I looked at, well, what about the combination of like +1 and -1? So what if I had something like sodium oxide, right? Sodium Na2O, where sodium has a charge of +1 and oxide has a charge of -1. I was interested and I looked it up. And the melting point of sodium oxide is in between that of sodium chloride and magnesium oxide, which you would anticipate. Right? It's got a slightly higher magnitude of charge. Melting point is 1,132 degrees Celsius. So you can see that according to this example, it is possible to rank these substances in order of melting point just based on that magnitude of charge, right? Pretty cool, I think. Now, is that true in every case? No, because it probably comes down to some other stuff too. But this example does happen to work out nicely. And any example that you would see from College Board would work out nicely. They would never give you something that you have to deal with multiple factors. That's what we mean by the higher the magnitude of charge. As we also know, the closer the ions can get, or in this case, the distance between two particles, the stronger the forces are between them. And we're going to talk about that in this last example here. So like I told you, I did this before and I didn't even bother to get rid of the definition for lattice energy. But lattice energy is the energy required to separate 1 mole of an ionic solid into gaseous ions. So let's say I have NaCl, solid. And if I break that up into its ions, into gases, Na plus 1 and Cl minus 1, it takes so much energy to do that. And that energy is what we call the lattice energy, okay? Will College Board ever ask you to write that out? No, right? You'll never have to just write an equation for that, at least not that I've seen in my 3 years of teaching this. But just so you know, that's where we're getting this from, how much energy it takes to complete that process. And here are a whole bunch of lattice energies for different alkali metal halides. So as I go down this section, you see we have alkali metals. And they all have a charge of +1 because that's the trend with alkali metals. Whereas going across this way, we have all of our halogens, which all have a charge of -1. So this particular chart is telling us all of the lattice energies. It requires a lot more energy. Let's erase that right up there. It requires a lot more energy to separate lithium from fluorine than it does from cesium and iodine. This is not as a result of the magnitude of charges. This, however, is a result of how close the particles can get to one another. We know it's not because of magnitude of charges because all of these examples and combinations are all +1 and -1. So they have the same magnitude of charge. So why does cesium iodide have such a lower lattice energy than lithium fluoride? Cesium has 6 shells around it, whereas iodine has 5 shells around it. So 6 shells and 5 shells, think about how big those atoms are. Those nuclei can't get that close to each other. They're too far apart because they're literally too big of ions. As a result, it does not take as much energy to separate those particles from one another compared to lithium and fluorine, for example. Lithium and fluorine both have only 2 shells that surround their nucleus. Lithium and fluoride could get so much closer to one another because of that. And because they get close to one another, it's much more difficult to separate those ions. So this right here, lithium and fluorine, these have a very high lattice energy. And that's because these have the smallest ions. Whereas here, we have the smallest lattice energy. And that's because these are the largest ions. All has to do with size here. That's because your magnitude of charges are the same. So, and you can see there's a nice little trend as you go up and over, right? So cesium to iodine, it's the lowest, and then it starts to get progressively higher as we get to smaller ions in the opposite corner. Let's start wrapping this up. So higher lattice energies typically result in higher melting points and an increased hardness. because more energy is needed to overcome the forces that hold the ions together. So typically, your substances that are very close to one another, or that have higher magnitudes of charges, they are going to have higher melting points, and they're going to be harder. And that's because the forces of attraction between them are a lot stronger. As always, if you have any questions, please make sure you ask me. Hopefully the rest of the videos for this unit will be relatively short. And I hope to fly through this unit probably pretty fast. Hopefully it's the fastest one we go through. As always, I'll see you in the next video. Have a wonderful day. Bye.